Welcome to the fifth lecture of the lecture series on fluid inclusions in minerals. In the last few lectures, we got ourselves briefly introduced to fluid inclusions, how they are trapped in the host mineral, because they are trapped as sealed cavities in the solid lattice of the host mineral, and we have been trying to understand the basic mechanism of how these tiny cavities are encapsulated within the growing mineral from the when it grows from the fluid phase or it grows in a constant medium. And we have had a brief look through some of the images of fluid inclusions from various types of occurrences like quartz veins in different types of mineral deposits, from migmatites, from ore minerals, from silicates, from minerals like like anhydrite and have seen the wide possibilities of shapes and sizes that these inclusions can display when we observe them under the microscope. We will again have a detailed discussion about how to prepare the samples for the fluid inclusion studies, but for the time being with this much of background information on the fluid inclusions, and when we move over to subjecting these tiny objects to various types of studies, beginning with trying to retrieve the information in terms of the physicochemical parameters like pressure, temperature and composition of the paleo fluid through systematic study. So, it would be good to just have to ask ourselves a few questions that there could be many more, I understand. So, whether we have seen that the inclusions display a wide range of sizes as low as less than about a micron, that is observable in a normal transmitted polarizing microscope, where we can go to magnifications sometimes at the most of 600 times or 1000 times. As we know that higher the more the power of the objective, the resolution of the image generally becomes a little less, and conveniently we can see these inclusions when we see them under in a transmitted light microscope with magnification ranging from 500 to 600. That means using a 50x objective with a 10x eyepiece or a 12.5 eyepiece. So, we have seen that these inclusions range in size ranging from less than a micron to more than about 100 microns, or there is actually no maximum limit, but this is the general scenario. And we know that the inclusions get trapped in the host minerals at different stages during its primary growth, and also any time afterwards the mineral in a vein or a rock, after it is formed, it is subjected to later deformation in the brittle or the brittle ductile deformation zones, and later fluid percolates through them, and later stages entrapment also take place in these inclusions. So, we ask ourselves whether there is any correlation with this inclusion size and the parameter generally which we see in the context of the aqueous inclusions, aqueous biphase inclusion, which is a vapor liquid and vapor situation, and we see that the vapor proportion visually differ in great ranges. At the same time, we are also reminded of the fact that we are able to only get a 2-dimensional view of the inclusions, which is actually in 3 dimension. It could attain any shape, any regular shape or any irregular shape, and we are able to see the vapor bubble. So, it might give us a false impression about the proportion of the vapor bubble when we examine them under the microscope. So, this is an important parameter which people used to use. The vapor by vapor plus liquid ratio V by V plus L, and in some literature you will find that this particular ratio is being labeled as the degree of fill, which is somehow analogous to a mass by volume kind of a parameter or a density, which we will discuss later. So, this as we have seen through the range, through the various the occurrence of the inclusions in various types of mineral host minerals, we find that actually there is no much of a relationship that could be observed between this vapor by vapor plus liquid ratio and the size of the inclusion. That could vary randomly. One large size inclusion visibly having a small vapor bubble and a small size inclusion with a large vapor bubble might turn out to be the same when we retrieve this parameter by systematically after our microthermometric experimental results, which we will discuss, and there does not seem to be much of a relationship. So, again we could ask, is there any relationship between size and the time relationship of entrapment of fluid inclusions, because there again the fluid inclusions are entrapped during the primary growth of the mineral as well as any time later. So, is it that could there be a relationship between the size and the time of entrapment? We have seen that even when they are occurring as part of the random 3-dimensional network, there is a variation in size from very small to very large. Even when they occur as trail bound or on as heel cracks, the inclusions when they get entrapped during the process of healing of the cracks by later fluid, there also we see that the variation in the size is quite significant. So, there does not seem to be any relationship between the size and the timing of entrapment of the fluid inclusions. Here we also ask ourselves, because we have seen inclusions which look to be sometimes pretty regular in their shape, conforming to a circular or a oval or elliptical or a negative crystal shape, and we have also seen inclusions which look to have been undergone a change in their shape, and sometimes. So, this rather conforms to our general observation that the larger inclusions, the inclusions which are generally greater than 20-30 microns or even more than 40-50 microns in their maximum dimension, these inclusions are the ones which are more prone to getting changing their shape of them, attaining any kind of a hook shape or an annular shape, which will be a point of our discussion when we go to the very important topic of re-equilibration of these inclusions under changing conditions of pressure and temperature or any kind of a disturbance or later disturbances that we can visualize happening in a geological environment. Okay. So, with this kind of background information, as we have been discussing, that we subject these tiny inclusions to various types of experiments, microscopic as well as microscopic experiments and microanalytical techniques. We say that we are sampling the paleofluid, the fluid which was active in distant geological past in terms of hundreds of millions of years or thousands of millions of years to even very recent. We intend to retrieve information on the physicochemical parameter like pressure and temperature, compositional characteristics of these fluid inclusions. Now, when we are attempting to do that, it is very natural that we have to take some assumptions, and the number one assumption is that the entrapment is homogeneous and the fluid that was entrapped is essentially the representative of the same fluid mass. That means, the fluid that we visualize that to have operated in any geological environment in the subsurface, and the sample that we see in the inclusion in the mineral as the tiny inclusion is actually representative of the paleofluid, and the entrapment is homogeneous. And the second assumption is that the inclusion behaved as a closed system. So, here it is very important because we think that this inclusion is trapped say for about say 1,000 million years back. So, since its entrapment till today, it has remained there as a as an entity So, if there are indications that the content of the inclusion has been changed, somehow it has exchanged material with the surrounding, then a whole of our exercise will become futile. So, this is a very important assumption that we make, and in any scientific investigation the basic tenets of the subject, that we definitely go with some set of basic assumptions, and it goes without saying that such kind of assumptions will be subjected to critical assessment, questioning, and again reaffirm such assumptions, that how far these assumptions are valid, or under what kind of situations such kind of assumptions will become invalid, or how to take care of situations where these assumption or this system seem to have violated these particular assumptions. We will be discussing them all, but in the majority of the cases this assumption holds good. The inclusion once trapped behaves as a closed system, means does not exchange matter with the surrounding, and that means nothing is added or subtracted from the cavity. And then the another important assumption is that this cavity once entrapped, it behaves as a same volume, the volume remains constant, it behaves as a isovolume isocompositional system. What we basically say that it is isochoric, which will explain what it is. Basically the word has come from this isochoric, means actually what we are, isochore is essentially meaning that the system has behaved as a the composition has remained unchanged, the volume of the cavity has remained unchanged, and it is even though we know that this inclusion was trapped at a condition which is pretty different from where we sampled it, means we sampled it almost near the surface, and the mineral in its surrounding in a rock or in a vein which formed at a greater depth at a pressure temperature condition which is different from, and then it is evolved through the decrease of the pressure and temperature, and that particular inclusion cavity within, talking of the individual inclusions, although we know that they occur in huge number, in millions. So, each of them has evolved in a constant density, constant composition path. Okay. So, if we just try to examine, our first assumption is that the entrapment is homogeneous and the fluid entrapped is representative of the sample fluid mass. If we without getting into much of the details at this particular moment, if we think that let us try to examine our assumption that this fluid, this small mass of fluid which is encapsulated is an inclusion cavity, is it representative of the fluid from which it formed? So, if it is not, what are the possibilities? So, what people propose, what or the way the discussion is sometimes made is there is something like a boundary layer effect. For example, we have that this is a substrate and we have some kind of an open space where the crystal is growing, and let us say that the crystal is growing from here and in a manner that we showed before, that it will grow layer wise. So, the thing is that the immediate contact, immediate interface of the liquid and the solid, and as we know that if this is the fluid medium, the constituents are actually being transported from the surrounding, diffusing through the fluid and is coming to the front on which this crystal is growing. So, in this process it is quite possible that there could be some kind of a concentration gradient which will be existing there, and the fluid considered at a very small scale, just at the interface of the liquid and the solid, its composition might be a little different from what is the bulk compositional characteristic of the fluid could be. Now, the thing is that it is not very well quantified as to what kind of a concentration gradient will be existing. Some amount of speculation are there, but in general it is, and in this context what is said is that if this is the crystal which is growing from the fluid, and this is the fluid, this is the medium, the fluid medium, then the inclusions which are trapped here, these inclusions which will be trapped here as the crystal will grow, if these inclusions happen to be very small, then the chances of the fluid encapsulated within these inclusion cavities being different from the rest of the bulk of the fluid is a little more. Whereas, if we think that the inclusions which are the inclusion which will be forming in this crystal and will be of reasonably large size, these inclusions is more likely to be representative of the paleofluid compared to the inclusions which will be much smaller in their size. And the another assumption that we have made, that the fluid is at the time of its entrapment is homogeneous. So, the other possibility that the fluid the situation might deviate from, although it, as we will see, in majority of the cases the assumption is very valid, but at places where the fluid is in an immiscible regime, that means mutual solubility of the two phases that we will be considering is negligible, is less, or actually they are immiscible, then at any point of time in a growing crystal, for example, if for example, if there is a crystal which is growing and the fluid there, if we are considering about the fluid to be water, then this representing vapor bubble and this dots representing the liquid, that means the surrounding liquid, the surrounding fluid is actually in a inhomogeneous condition, that means the existence of liquid plus vapor. So, there is a possibility that the growing crystal, which is the crystal is growing in this medium, will entrap a combination or a mixture of a little bit of liquid plus vapor. Even though we will see the inclusion as a biphase inclusion as we have seen them, liquid plus vapor, but this particular inclusion will have a history that during the entrapment it has actually entrapped small amount of some amount of liquid plus vapor together. The explanations sometimes if that is the situation, then our microthermometric experiments intending to retrieve information on the temperature of this fluid will become invalid, or we have to see that under that circumstances what are the measures we can take for such corrections, or what kind of other inferences which you can make from this situation. Okay. So, the second one, that the inclusion behave as a closed system, nothing is lost or added from the cavity. So, they though it is assumed, though this assumption is mostly valid in most of the cases, but under certain circumstances there is a suspicion which grows that well the inclusion cavities, once they are trapped, they might have, there has been situation in which they would have lost, they would have exchanged component with the surrounding, either loss or gain. So, this could have happened in when this initially formed mineral in the particular rock or a mass of vein is actually emplaced in a crust, in a different crustal environment in terms of the physicochemical parameters, and there may be a concentration gradient which may be established, or something kind of a pressure gradient which could also be established, which will allow for change in composition of the fluid which is encapsulated within the cavity. And there is another situation in which the fluid might not behave as a closed system, that happens during the process, which is, and the other situation in which this assumption, this important assumption might be violated is sometimes which corresponds to a situation where the inclusion might neck down. So, what we essentially mean by necking down, if we have originally a fluid which is entrapped, a homogeneous fluid, and either of the situation that it has already formed, it has already evolved into a two phase situation as a liquid and vapor, or it has remained as the same situation as liquid, and this particular inclusion will get necked down to two components, finally two individual inclusions, inclusion 1 and inclusion 2, and if it had a vapor, then they will have an disproportional splitting of this vapor, and in that case the original composition of this particular fluid inclusion is lost. In the other case, if the necking down of the inclusion takes place when it was actually in the one phase state, and then it evolves into the two independent inclusions, inclusion 1 and inclusion 2, where they also do have a situation where it is liquid, this part is vapor, this is liquid and this is vapor, and this is also, in this case, this is liquid and this is vapor, then these two inclusions are more likely to have preserved the original composition, and this assumption will be valid in the situation where the necking down took place after the vapor phase separated out of the inside the cavity as a post entrapment change. Then in this case the assumption will actually become invalid. So, there are ways and means to establish such a kind of process and to take the measurement on those fluid inclusions where we could ascertain that such kind of assumptions actually will be valid. This is also a very important assumption, that the volume of the cavity has remained constant since the entrapment, and the inclusion followed a constant composition, constant density, isochoric path with decrease in pressure and temperature since the entrapment. This is also valid in majority of the cases, as we will be shortly discussing about this situation. And there are situations in which the fluid inclusions after their entrapment would have traversed a path away or deviating from their isochoric path, and we will see under such what kind of conditions it might happen. So, there must be some kind of perturbation, either thermal or load, the temperature and pressure conditions which could have fluctuated or could have become different from what could have been a path of a constant composition, constant density path. This particular assumption is of course is very obvious, that whenever we do this fluid inclusion studies, we presume that we are actually talking about the fluid that was prevalent in that particular geologic environment. So, the relationship between actual trapping event and the geologic process of interest that we know, and this relationship in a way actually we try to establish this relationship, and sometimes even we sample the several generations of the fluid within the same host mineral, as we have discussed before. The several generations of fluid might have acted at a very close time interval where the compositional characteristics would not have changed much, and then it is possible on our part to actually reveal or actually work out the evolutionary path of the fluid that gave rise to this particular feature, either an ore deposit or any kind of a interaction with rock. So, this assumption is very much there in our mind, and we only have to change or it will be all basically on the interpretation that we will be making from the results that will finally decide that whether this the fluid that we have sampled is actually is related to the process that we are talking about, or we are more interested to work out. So, now coming to the very important topic, we will be discussing this again and again during the course of our lecture, and this is one of the very important aspect of fluid inclusion study, that the inclusions that we classify them as primary or secondary. Here we are using another word as pseudo secondary. So, pseudo secondary, when we use a word pseudo secondary, means actually meaning is that it is actually primary, means we are talking about broadly two categories of fluid inclusions that we observe in the minerals. One we can say they are the primary inclusions, the other ones are the secondary inclusions, and we believe that it is the primary, we are interested in the primary fluid because we want to know the exact condition in which the particular mineral has formed in nature. Although many of the situations, as we discussed before, a fluid that just acted a little later than the, or there are in a sequence where a hydrothermal vein was forming with continued fracturing and fluid activity, there the different the subsequent stages of fluid activity could actually represent one and the same fluid. But in the other situations, the fluids that we see as secondary, or the fluid that acted later on, could be apart by several hundreds of millions of years, and they would totally be unrelated to each other. So, then the crux of the problem is that how to distinguish between these primary and the secondary inclusions, so that the data that we retrieve, we can treat them with that much of caution in our mind, that what kind of fluid which actually we have sampled. So, quickly going by the points, that the inclusions which essentially will be a part of the three dimensional network, not following any linear array or kind of the heel cracks, going traversing through many of the grains in the mineral of the mineral host mineral, and they must be present in primary growth zones, which we have also seen through photographs. They should be isolated in their occurrence, not as trails, and away from the nearby inclusions by at least by 5 times the diameter of the inclusions in of the observation. These 3 points are these 3 points are actually much more definitive and important. Sometimes size or the shape is also associated with their primary or secondary origin, but they are sometimes very misleading, as we have seen that a negative crystal, a host like mineral like quartz has very rare negative crystal shaped inclusions, whereas a mineral like anhydrite where we see that the primary as well as the secondary inclusions could be of negative crystal shape. So, this is not a very definitive criteria for primary and secondary, and as we discussed that in a particular growth process, the first stage of minerals which were deposited from the fluid could have undergone brittle fracturing, where the individual grains also would have undergone fracturing, and the later stage fluid would have just overgrown and overgrown on the existing crystals, and so we see sometimes we see the crystals having fractures within the grain. The fracture is not traversing through the adjacent grains of the host mineral, and in that case this is the one which here we actually reserve for the pseudo secondary inclusions. And we can only tell that okay, whenever there are inclusions, they follow trails, they are trail bound, they are transgranular, means across many grains. When we see them under the microscope in the field of view, we can tell them as secondary inclusions, or in other words we can broadly categorize the inclusions to be trail bound or non trail bound. When they are non trail bound, we have to be very sure that they are part of the 3-dimensional network, getting focused at different planes when we see them under the microscope, and they just do not follow any particular linear pattern in their occurrence, and then size, shape, and many of the parameters which can come later. Okay. So, if we just look back in this particular week of the discussions so far on the fluid inclusions, that it's let us recall that it is very important to study fluids, because there are wide spectrum of processes, are processes which are fluid assisted or result of direct fluid activity, and the fluid inclusions, they sample the paleofluid that operated, and they can be entrapped virtually in any mineral that forms, grows or recrystallizes from the fluid or in presence of the fluid, and the fluid inclusions by virtue of their distinct optical contrast are very easily identifiable. One needs to just have a proper magnification polarizing microscope and properly prepared sample. So, one can always see these fluid inclusions, identify them, and can subject them to various types of microscopic, microthermometric and microanalytical studies, and these information that they retrieve from them are very useful in addressing broader issues of art processes. The entrapment of these inclusions, the mechanism, are rather crudely known, and we almost in the process we always get our ideas refined the more and more information that we get from experiments conducted in different types of crystal growths, and more importantly, over the last 3 decades there have been substantial input coming from many laboratories in which fluid inclusions are actually trapped through experiments. They are called the synthetic fluid inclusions, and we get to know more and more about them, and making this particular study of inclusions is more and more meaningful and more definitive, and the diversity in the composition of the fluid inclusions, they give the first hand information about the evolution of the fluid in any situation, and these tiny entities, the fluid inclusions, which are sealed cavities in the solid lattice of the host mineral, they should be meticulously studied, categorized and experimented, and the following lectures will actually be discussing them in greater details and taking up specific situations where and then the principles that we will be requiring, we will be discussing them in details. Thank you.